next presenter is Armin Shomohammadi, who has a master's degree in railway engineering from the Iran University of Science and Technology. During his master's thesis research, Armin investigated the effects of undersleeper pads and deconstructed tier undersleeper pads on ballast degradation and settlement. He has successfully worked on large-scale civil railroad and infrastructure projects such as ripraps, railway culverts, railway switches, and crossings and ballast tamping for the Railway of Iran. Please join me in welcoming Armin.
Hello.
Hi.
Can you confirm you have my audio and screen?
Yeah, looks great.
Thanks. Thanks for your introduction. Hello, dear attendees. My name is Armin Shomohammadi. It is absolutely a privilege for me to be participating in this prestigious conference with professors, researchers, and rail experts today. I wanted to appreciate the conference organizers for inviting us to have the chance to present our research. Our paper entitled Laboratory Investigation of Mechanical Properties of Used Rubber Tires as Undersleeper Pad in Railway Tracks have been carried out with collaboration of Iran University of Science and Technology and Széchenyi University of Hungary, and supervised by Professor Morteza Ismail. The content of my presentation is demonstrated in this table, which commences with enumerating of the literature survey on undersleeper pad, end-of-life tires, and deconstructed tire USB. Further on, we have a procedure diagram, utilized material and methodology, results, and discussion respectively. At the end, we have the conclusion remarks prior to acknowledgements and references. Plastic elements are the most efficient components for establishing and changing vertical stiffness, reducing noise and vibration in railway tracks. Using specific rubber pads in railway tracks as a solution has received special attention for researchers and industries. These pads include fastening system plates, USB, UBM, and rail rubber pads. USBs in particular, for more than 20 years, have been utilized in railway tracks, especially in high-speed rail lines. The most relevant previous literature reviews on USB end-of-life tire and constructed tire USB and DT USB are listed in this table. Zucker et al. Showed USB's best performance in decreasing the vibration occur at the 50 Hertz by 6.7 decibels and seem to have some negative effects at lower frequencies. UIC research demonstrate virtually similar results and show USB's decline in ballast settlement efficiency. Thompson Gupta estimated that the rate of tire production will have risen and passed 5 billion by 2030 worldwide. Therefore, researchers like Sanchez et al. Commenced conducting tests to analyze the feasibility study on ELT use as DTUSB and showed a 5 to 11 millimeters thick DTUSBs seem to have the best performance and to meet optimum stiffness. However, the gap we decided to fill and investigate more in depth was the necessary tests for primary and high-speed rail tracks, which were not carried out and only conducted for tramway and underground tracks conditions for the feasibility study. Here is research procedure diagram. At the first stage, materials used in laboratory tests comprised of DTUSBs and concrete samples as a substitute for the sleeper will be demonstrated afterwards. The research methodology, meaning how to conduct static and dynamic bearing moduli, will be discussed. Finally, we will have results on different specs. By evaluating different standards, the USB associated standards, we chose to go with the Dean standard for validation and compared with other literature reviews, research. According to Dean standard, as we can see here, the D2USPs with the given area dimensions and different thicknesses of 7, 9, 11, and 30 millimeters, and concrete sample with the same area of the pads and the height of 200 millimeters were subsequently utilized for the tests. And turning to methodology, the first test was conducting the static bedding modulus or static. Table 3 demonstrate the required imposed loads to calculate it for 4 types of tracks. There are 4 steps to measure C static. And to begin with, the force is calculated for any range of loading and with the application of loading range of sigma U to sigma 0 and the rate of 100 newtons per square millimeter per second. The stresses and settlements were recorded at the third cycle loading cycle, and C static is calculated for stresses and ranging sigma 1 to sigma 2. The second test was dynamic bedding modulus. The imposed loads to calculate C dynamic are given in table 4. And for measuring C dynamic 1, at each test frequency, the pressure after a 3-minute rest time at sigma 1, the data was recorded after 10 seconds of applying dynamic load. 10 complete cycles were performed for each frequency. Finally, for each frequency, C dynamic 1 was calculated out according to equation 3 in the third cycle. The average results of 3 tests were recorded for both C static and C dynamic. And the results have been analyzed, and the line graph of C static 1 and 2, which is defined in table 6, that they are different C statics according to their pressures imposed for medium compaction and high impact compaction of ballast for main railway tracks is provided in figure 5. As expected, by increasing loading range due to the higher compactions of ballast according to the Dean standard, from medium to high ballast compaction mode, higher C static values were obtained. On the other hand, the thinner these pads, the higher the elasticity modulus we calculated. According to Dean standard and obtained results for medium ballast compaction, all thicknesses of and for high ballast compaction, the D2USPs with a thickness of 7 mm are classified as soft pads, and they will be suitable for decreasing vibration and stresses induced by train. Compared with Sanchez et al. Research results of the same parameter, trends and figures for the same thicknesses matched and are comparable. Moving on to the C dynamic 1 for frequencies of 5, 10, 20, and 30 Hertz versus thickness, the results are demonstrated in this figure. The graph reveals that C dynamic 1 moderately fall by increasing pad thickness, and the higher the frequencies, the more C dynamic values attained. Although the noticeable point is for pads with higher thicknesses of 10 millimeter, the values of C dynamic for frequencies of 20 Hertz surpassed that of 30 Hertz. That could be extended in further investigation. Compared to results of Sanchez et al. Study again, trends and figures for the same thicknesses are similar and follow the same rate. And the last parameter the dynamic stiffening ratio, the ratio of C dynamic 1 and C static 1 has an upward trend contrary to two prior parameters. It is apparent that by increasing thicknesses and frequencies, the dynamic stiffening ratio rises at almost the same rate. And moreover, follows the results the Sanchez et al. Book, and for this parameter as depicted in figure 10. And here are my conclusion remarks. First, the thickness effect significantly impacts the pad's static or dynamic performances, which is evident by evaluating the pad's stiffness moduli charts. Thicker pads tend to demonstrate higher flexibility, while the thinner pairs have higher elasticity modulus. Subsequently, the second finding is that according to DTUSP's static test results for medium ballast pressure, pads with 7 to 13 millimeter range of thicknesses, and for high ballast pressure and compaction, the 7 millimeter thick pad seem to have the capability to decrease vibration and stress induced by a train. Finally, the examined pads are highly likely to be suitable for main railway tracks. And in the end, I ought to mention here what remains to be known is whether this end-of-life tire USPs will have a negative impact, such like reducing lateral resistance of rail tracks alongside the benefits they bring. And if this topic interests you, I highly encourage that line of inquiry as we continue to address this important issue in further investigations with different study aspects like numerical analysis, like discrete element methods and site tests in various conditions, including implementation of these pads in cold regions or even other types of tire-derived resilient components, such like tire-derived aggregates and recycled rubber mats. And thank you for your interest and attention in our study. And I would be glad to hear your question and comments.
Thank you so much, Armin, for that great presentation. We do have a couple of minutes. There is a question from Reza. Reza, if you want to unmute yourself.
Okay, thank you. Can you hear me, Armin?
Yeah, clearly.
Okay. Thanks for your great presentation. I just have a quick question about the lateral resistance and also the damping for the vibration, because when we use under slipper pads, especially when we have some freight track or also high-speed track, there would be some concern regarding to the lateral resistance and also lateral forces. But I just have a question that, do you consider this into your consideration? I mean, do you take this into your consideration or not? And also, what about the damping vibration? Because when we use something like rubbers, the tires that you said, there would be a problem by the damping. For example, when we use them on the bridge or some stiffer parts, there would be some concern to transfer the vibration directly from the ballast to the substructure. So do you actually work on these matters or not? And many thanks for your great presentation again.
You're welcome. Thank you for your great question. And actually, I've done some research on the damping ratios of these kind of pads in another study that you can find in my Scholar or LinkedIn. And I worked on ballast bags and with the ballast and implemented these USBs on the top of that. And we calculated the damping ratio, the ballast breakage indexes, and the other indexes that will be useful for further investigation. And about the first question about the lateral resistance, there have been some research about these USBs and DT USBs about the lateral resistance and the negative aspects actually of these pads. But I personally did not extend my investigation toward this issue, but maybe in the future I will consider it in my thesis, in PhD thesis, or moreover.
Perfect. Thanks so much, Armin. Yeah.
You're welcome.